Before we get started, get your model kits. If you don't have them, stop and get them. You need your model kits to follow along properly with this lecture. So sit up, get your model kits, and build ethane. Go. So when you built ethane, you could see these bonds freely rotate. Remember, sigma bonds are made from end-to-end overlap, right? To make that from the hybrid orbitals. And they're not restricted to parallel overlap, which p orbitals require. So you can't rotate around pi bonds because those p orbitals wouldn't be out of alignment, but sigma bonds, no problem. So you can rotate freely, which brings up the point that how I built ethane might be different than you did, because you might have built one with a rotation in the back to be perfectly aligned or maybe perfectly offset with the carbon in the front. These are called conformers or conformational isomers. And that's the topic we're embarking on now. We've only scratched the surface of 3D analysis, so models are very important to help make this a little bit quicker to grasp. So make sure you do have your models. Okay, so as the pictures indicated here, this is drawn using Spartan. These are the two main sort of, these could be upside down, or I'm not counting all those sorts of where the entire molecule is rotated. I'm talking about where one piece is held fixed and the other is rotated. So for example, look at this methyl, where there's one hydrogen kind of going up. If you rotate around this single bond, then that hydrogen going down would actually now go up, right? So if you do a full rotation. But there's many rotations. I could have this hydrogen, instead of being in the plane, these pieces are in the plane, it could be a dash or a wedge, right? So it could trade all of those places. In fact, when you look at grab your ethane model again and rotate one of them, you see you can actually make a full circle. So there's 360-degree rotation possible with respect to the other carbon. So we're going to be analyzing that conformational analysis. So the two opposite sort of conformationally opposing methyls here, where one has the methyl and the hydrogen in the plane going up, the other has the hydrogen that's in the plane. Hopefully you see what I mean by in the plane, right? Like if this was a piece of paper, these would be the planar pieces, not dashes or wedges, whereas this would be your dash and that'd be your wedge. So let's actually convert this 3D drawing to an actual VSEPR structure with the dashes and wedges. So those H's would be my sigma bonding framework that's planar. But then this carbon on my right would have one H that's a dash going up, one H that's a wedge going up, and then this carbon here would have them pointing down. Wedge coming out, going down, wedge dash in the back going down. And then let's compare that to, so let's convert those to bond line format. Notice the one right here did not change for rotation. So that makes it easier to keep one fixed, because if you're rotating them both willy-nilly, it's hard to really analyze what the new change is. So if we keep one fixed and rotate the other one, then we can kind of compare the effect of that. So notice here's my sigma bonding planar framework. So there's an H in the plane, there's my carbon, and now instead of going down with the H, it's going up. See, we used to have, this was my planar piece, now here it is. It's got this sort of U shape. Right here, that's zigzag sort of shape. So, right? So now what I'm going to do is finish that, drawing that in. Notice that both of the non-planar hydrogens, the ones that get the dashes and wedges, are going below those carbons. So wedge, wedge, dash, dash below the carbon. So they're going to be pointing down this way. Wedge, wedge, dash, dash. Okay, with lots of practice of drawing these tetrahedral carbon centers, we should start to see that pattern, that if the carbon that's planar is, essentially pointing down, see how that vertex kind of looks like a down vertex? the dashes and the wedges point down. If the carbon that's planar points sort of up, like this one, notice how that vertex goes up, the dashes and the wedges go up. So let's highlight that planar part just so we can kind of emphasize what's in the plane. That always makes it a little easier to track. So that's where this piece came in versus. Now do that with your model. Look at the one where we have sort of the planar pieces. If you could slice a plane through the carbons. These are conformational isomers, or also known as conformers. Get my pen. Conformational isomers, aka conformers. All right. What is the difference? It's the planar relationship, right? Not only that, look at how none of the H's line up here. There's on this carbon, the H is in the plane, but the H that's in the plane is down. The H's that are out of the plane are up here, the H's that are out of the plane are down here. Whereas here they perfectly line up. Just superimposed, if you will, on the dash H is another dash H, right? So what we could actually do is see this alignment more easily from a different perspective. So getting my model back, and you'll do this with your model, take your ethane model that you've had side to side, turn one of the carbons towards you, and look how different that looks. But we could see that if I let the green ones be the ones that are hydrogens that are in the plane, when they're on opposite sides, like that zigzag style, see that planar framework zigzag, and I rotate it here to look at it. And then I rotate it down so I'm looking down a bond, so are you. We could see that they're on opposite sides. But if we rotate to bring them onto the same side, everything's lined up. They're aligned. We call that eclipsed. When they're not lined up, we call that staggered. Furthermore, the fact that these are on opposite sides, the ones that are my point of reference, we say these green ones are anti to each other when they're completely opposite sides. But there's lots of ways to have eclipsed and staggered. So those are the two only positions we're going to look at. Eclipsed, staggered. Eclipsed, staggered. Eclipsed, staggered. Ethane's a good one to start with because it's simple. They have no energy difference between other eclipsed and staggered. So eclipsed, staggered, eclipsed, staggered, eclipsed, staggered. So because they're all H's, our only two options are eclipsed versus staggered. So which one's which? What we're going to do is we're going to use our eye to look down there. So what I did is I turned the model toward me. In paper, you can't do that. You can't easily turn a model towards you. So you have to kind of pretend your body's in the plane. You can actually keep them on paper. You've decided to keep the molecule fixed, but your body is essentially pretending to move. So the fixed point of reference is the model. When we play with models, we are the fixed point of reference. We keep ourselves still and we move it how we see fit. When we're working on paper, the model is fixed. We move. So we got to kind of visualize our eye right there. And when you pretend you're in there like that, or like that, it could be either side. I could have put my eye here or here, but we line up so that we are looking down a carbon-carbon bond. And when we do that, we will see this. Okay, so let's do that. Let's be consistent and do it from the same side since we're comparing both of them. Okay. But like I said, I could have easily picked the other side. It's just as long as you look down, a carbon-carbon bond. So it involves two carbons. All right, so we're going to get comfortable with this perspective. This is called a Newman projection. There's a specific way to draw it on paper because you can't always produce these Spartan molecular model calculated structures, right? So, but this is for the sake of seeing it in 3Ds, this is what it looks like now that we've, if we were able to hop into the screen or the paper and put ourselves right there, we would see this for the first case and this for the second case. Now it comes much more clear. This is why we like this point of reference, this perspective. It becomes much more clear what's going on. We can see much more easily that these H's are all out of alignment, and here they are completely aligned. Okay, so this is called the staggered conformation. And this is the eclipsed conformation. To draw this on paper without using fancy modeling programs, you draw a circle. Okay, this is the atom closest to our eye, so our front carbon. Behind that circle is the other atom, okay, that's further from our eye. So this would be carbon 1, and behind it would be carbon 2, 1 and 2. And if we go back to our reference 1, since we decided to look from here, that's carbon 1, that's carbon 2, 1, 2. Call it AB, doesn't really matter. We're not trying to use an IUPAC naming system, we're trying to label and track. At least not right now, we're not trying to name. Okay, so let's produce those into Newman form. So staggered has the front carbon, should have 3 bonds coming out of it, and the 4th bond is that bond going into the plane of the paper, piercing it to bond to the other carbon. So you don't see the 4th bond drawn because it's literally going down out of the plane right there, okay? So we have only H's since it's ethane. This is carbon 1. Carbon 2 is in the back. And notice what we're going to draw our H's this way. So the front looks kind of like this little like Mercedes-Benz symbol here, right? But I like to also kind of think about it as like a Y shape. So it looks like an upside down Y. And because it's staggered, we have the opposite. We have the right side up letter Y there. So let's put those, fill those in. Those are all H's. Okay, so in order to get from staggered to eclipsed, we had to do a rotation. Okay, so when we rotate, we get to eclipsed. I'm going to keep the front the same because that's what it looks like here. See this framework here? Looks the same. And this is hard to draw completely eclipsed bonds. So we just draw them kind of offset just a bit, but the understanding is that they're eclipsed. Because if you turn the model just a little bit, then you could see them kind of offset just a bit. Okay, so that's the eclipsed. Let's label our staggered and eclipsed up here. So I'm going to make this a little smaller. So from this perspective, this was our staggered. This was our eclipsed. So these are related by rotation. So in other words, these are the same conformer. They're the same molecule altogether, but when you're talking about conformational isomers, then in terms of one's different conformationally than the other, we have a staggered versus eclipsed to talk about. So this is an important term. You want to be able to recognize which ones are staggered or eclipsed. Those are only 2 options with their relative orientation. But that's in the case of ethane. There's only 2 types of staggered eclipse, but there are many, many ways to arrive at that, because we could have started here. And like I said, was that 360 circle. So we had 1 staggered, another eclipsed. So that's the second eclipsed. Staggered again, another eclipsed. Staggered again, another eclipsed. There's 3 staggered and 3 eclipses. When the groups are not all H's, that makes a difference. So ethane is not going to, that's by far the most simplest case scenario, right? when are we ever going to have only H's attached? We're going to always have usually another group. It's a good one to start with just because it's a difficult concept at first, but it's time to transition to the next level. Okay, so first we're going to establish a generic template, and then we'll do another real example with a bigger molecule. Let's look at this molecule. It's a little different than ethane. There's 2 carbons. However, now there's 2 different groups attached. They're not H's anymore. So just let, in fact, in Spartan, this one's bromine and this one's chlorine, I think, which is why this bond is longer. But we'll just call these X and Y so that we can apply this to, what if this was a methyl and an ethyl, or a phenyl and a butyl, right? We're just going to generically treat red as one group that's different than the green group, and definitely not H. So we'll call this X and we'll call this one Y. Okay, so as we decide to look at this from the Newman projection perspective, let's do our I in the same spot. We're going to look down carbon 1 to 2. And that means if you have the model ready, you turn it around to look at it, right? And you see all the different possibilities. A table and label those, because now we have more things to describe. Okay, so one scenario, and that's where we have the 2 groups that we can assume are bigger than H, because H is actually small. So this is actually the ideal scenario, is that these groups are opposite each other. So remember, we're going to call this X and Y, X, Y, X, Y, and X and Y. Okay, so we can have them opposite each other, and that would be staggered, because notice how these other groups are not eclipsing them. Now we have eclipsed, right? So let's staggered. And eclipsed. I said there were 6 ways to do it. What 2 are missing? 2 are missing because they're equivalent. So I only went around one side of the clock, if you will. So notice you have opposite, then it's working its way toward it, eclipsed, then rotate another 60 degrees, it's toward it, rotate another 60 degrees, then it's here. If we were to continue rotating 60 degrees counterclockwise, we'd end up with the green sphere here, which energetically would be the same as this one, right? We'll see why soon. Okay, so I've also done the work to translate these to Newmans for you, but let's go ahead and make sure we follow it by tracking them with some color coding. So red was X. I'm just going to fill in those colors to make it easier to track. And green was Y. So I'm going to find all those Y's and circle them green. And the red, look at, they're getting closer. Y is getting closer, and it's finally eclipsed. Okay, so when X and Y are as far away as possible, which is desirable because X and Y will always be bigger than H. H is the baseline for the smallest thing, and you know, things repel each other. They like to be situated farther apart. So when x and y are as far as possible, there's a name for that. That is called anti-periplanar or anti-coplanar. So it's kind of synonymous. I'm going to write here, anti-coplanar, aka anti-periplanar, which, by the way, sometimes we just say anti, but the coplanar part becomes significant later. They're in the same plane, which allows orbital overlap for future reactions, but we're not there yet. So we're going to recognize that they're anti to each other. Now, when they're opposite each other, that introduces a new term, a dihedral angle. And notice that you're used to doing angles with three things, you know, A, B, C, right? What's the angle? Right there, A, B, C. How do we get four things? Let me show you. If we want the dihedral angle of these two green spheres, just realize this is green screen, so they might not look green. How about we do the orange this time? The dihedral angle of the two orange spheres, see how they're opposite, just like the one in there? You could see from here pretty easily, they're 180 degrees from each other. How is that an angle? Well, we are treating the four bonds. We're seeing the atom or group in question, orange, carbon 1, carbon 2, atom or group in question, orange. That's why there's four. So there's always the group in question, carbon, then carbon it's the other one's attached to. So looks like we're trying to get an angle out of four, but we're actually just measuring from here to here, where these two carbons are superimposed to be like a single point. Okay, so we would describe those as 180 degrees from each other. All right, what happens now? X and Y are not 180 degrees. So what would that relationship be, the dihedral angle? Think about that. So if it was 180 here, where is it now? It's 60 degrees less than 180. It's now at 120. We're working around, basically we're working around a big circle, right? So right here is 180, if this is your point or starting point of 0. So right here would be 120 degrees. This would be 60 degrees. This would be 180 plus 60. So 270. Not 270, what am I thinking? 240. $300, and then 360 is the same as 0, right? Okay, so we work that out as 120 degrees now. So the X and the Y are eclipsed with H's. They are not eclipsed with each other. How about this scenario? So we can see this matches this, and we've moved it over 60 degrees closer to the X. So that's now, if this was the 0 degree point, from here to here is now 60. So it's 60 degrees separation. These are staggered, right? So this is a staggered conformation. But there's more detail we can get into when the groups are different. So this is staggered. This is eclipsed. This is another staggered. And this is another eclipsed. And we're trying to differentiate between the staggered and eclipsed because now that we're not using ethane, where everything's H's, they're not equal. This staggered is not the same as this staggered. Look at those are closer together. These are farther. This eclipsed is not the same as this eclipsed, where they are, the big groups are eclipsing. The big groups are only with eclipsing with H's now. Big groups are eclipsing with each other here. So we're going to spell that all out. Okay, so when they are staggered, yet they're not anti, they're adjacent. They could actually bump into each other if those groups are sufficiently big and cause a repulsive sort of interaction, something that's not favorable. So we actually can show that sort of bumping visual with these, sort of you imagine the electron clouds overlapping, which is undesirable. And we call this interaction gauche. But interesting enough, it just means kind of awkward. It's not favorable. So it's gauche for them to be next to each other. So these are staggered and gauche. Okay, finally we arrive at, hopefully intuitively, you can see that this is the least desirable of all. The two big groups are literally eclipsing with each other. So if they have the better chance of overlapping their electron clouds, or even worse, their groups of atoms. And so that's highly unfavorable. So this is eclipse, but it's eclipse coplanar because they're together in the same plane. So when it's eclipsed coplanar, that means they're eclipsed with each other. Now we've gotten to where they have since they're eclipsed with each other, that means they have a 0-degree dihedral angle with each other. Okay, so in summary, this table kind of summarizes some of it, but we know atoms and other groups of atoms from VSEPR theory repel each other. When two groups are forced into the closer proximity of each other by rotation, like that gauche interaction or the eclipse interaction, we call this torsional strain. That is not a desirable, it costs energy. If X and Y are large enough, then we will see a significant difference in the preference for some conformational isomers over another. So we have a problem to do here. So we can decide make these decisions, which conformational isomers are preferred. We're going to rank the ones we just put in that table from high to low energy. So in other words, less stable here, high energy, that means least stable, not preferred, right? And then we'll put the low energy down here. So that means more stable. And that's preferred. Preferred. That looks like a bad spelling, but I think that's right. Okay, low energy. All right, so the highest energy, hopefully we would see, is where the two biggest groups are on top of each other. Eclipsed coplanar. Avoid that when possible. Doesn't mean it doesn't happen. The next worst is actually all eclipsed or worse than all staggered. So, but we're getting closer in comparison here. Now this is a trend. Nothing is 100%. It's all a spectrum of probability. So could we have exceptions to this? Absolutely. So if the groups were enormous, gauche might actually be worse than some eclipse. But for the vast majority of cases, trends work, which is why we like to use trends. But we always acknowledge them. The smart thing to do is acknowledge that this is not a mold that's one size fits all. You still have to put some thought into why something doesn't follow the trend. That's an interesting problem, actually. So there are sometimes, but we see a trend and it feels good to see, oh, that fits into the trend, and that happens for 90% of the cases most of the time, maybe even 95, 96%. So that's our goal. We're going to be doing lots of trend establishments so we can make predictions. And then if we see it doesn't fit the trend, we'll try to understand why, but you wouldn't really know a priori why that happened, okay? Okay, so eclipsed, gauche. Next to each other, so the two eclipsed are worse than the two staggered. The most stable by far is the staggered that's also anti, which is anticoplanar. Okay, so when we are asking for the preferred isomers, you always want to go for anticoplanar if possible. And notice that these are the eclipsed variety. Okay, we're going to put this all together. I put an old exam question right here. And I'm going to have you give this a try. And you can check your answers. So you're going to complete. Notice that in this problem, you were told what perspective. So we're going to get big molecules and lots of carbons to choose from. But a Newman projection is defined as a viewpoint from one carbon to another. Any two carbons can have a Newman projection. It could have been this two, it could have been these two, it could have been these two. So you're constrained because that wouldn't match the answer key if you picked these two. You're told specifically to do carbons 3 and 4. And it says must be down the C3 to C4 bond. So that means down the C3, C3 is in front. So that means the I goes there. The I was actually pre-drawn for this exam to C4. So you're going to look here, and it was not uncommon in exam rooms when we had them in the lecture hall for the students to kind of get in there and envision themselves in the paper, as well as the model kits. Okay, models are allowed on exams. You don't want to be fumbling with them though. You want to be expert, know exactly what you're going to start using them for. So you could quickly build it and verify your Newman's correct. Just takes extra time. So you don't want to be doing that as a crutch for the exam. You want to be doing it as a crutch for understanding now and have some mental breakthroughs with your 3D spatial reasoning. Notice that the Newman is quoted as original, then most stable. So in other words, you are going to be tasked with drawing the original. I want you to get that far. I'm going to do the most stable with you after. So at least get to here. If you're up for a challenge, fill that one out too and answer the questions that follow. Okay? How'd you do? That's the thing with these Newmans. Watching me do it should actually be fairly simple. Doing it from scratch on your own is another story. So no pain, no gain. You got to make sure you get yourself to do that. Now, first things first, you know you're going to be doing 3D spatial analysis, and not all of the hydrogens are drawn, and those are going to be drawn later. They're going to be drawn on the Newman, so you might as well draw them now. That will make your analysis easier. Okay, so we are going to draw in the hydrogens. Let's do it. All right, so it's going to be a little bit easier if I just put it right here. And then I'm going to draw in the missing hydrogen here. Doesn't that make it a little easier? Now get in there and pretend you're looking at down that carbon-carbon bond. So if you do that, you know, in the beginning you might even need, looks kind of like an alien with one eye, but you might even need to draw some arms on there and say, okay, if this person was lined up, a little laser vision right there, with that carbon, where would that person's right hand be? Would it be a dash or a wedge? Would it be going into the paper or coming out? So the right hand from this angle, it doesn't mean the right hand is always this. From this angle, the right hand would be a dash and the left hand would be a wedge. That's just going to be true now for the rest of the problem. Okay, and notice the feet. The feet are really this, we're calling this group CH2, CH3. We're going to call that ethyl, ET. So let's make that the feet. Okay, so there's that ethyl group. It's pointing, it's below you, right? So your laser vision with that carbon, and you got to decide which is your right hand and left hand, but your feet, you know, are the ethyl. That's been started for you. Once you know where the feet are, you know, okay, this is an upside down Mercedes-Benz sign this time. We got the, in other words, it shapes like a Y, like the letter Y. And That's just the first carbon. This is carbon 3. Carbon 4 is in the back. How are we going to draw carbon 4? Well, notice that carbon 4, look at its planar group. I'm going to call this propyl. Let's abbreviate because it's 1, 2, 3, right? I'm going to abbreviate that PR. So the propyl group is on the same side as the ethyl group. They're both down and they're both planar. In fact, we have that, our two options for the sigma bonding framework that's planar is that zigzag shape or the U shape, and we have the U shape. That only happens when they're eclipsed, right? Do you see how they're in the same plane? There's two wedges pointing in the same direction. They're on the left. There's two dashes pointing in the same direction. They're both on the right. So we have an eclipsed situation, which means you draw that back carbon set of bonds right here, like so. Okay, let's fill everything in. So we decided left was the wedges, fluorine, and so in the front carbon, carbon 3, that'd be fluorine. That means H is on the right. We also decided in the back, the left was the wedges, so that's the H in the back. That's the one I drew here. And this is a methyl. I'm going to write methyl just so we don't get confused. That methyl is going to go right here. Okay, now this is conformer A. It is, there's a hint, this is not the most stable conformer, but you should know that because they are eclipsed, right? So of course it's not the most stable. We must rotate if we want to see the most stable. So as drawn, our first result is not the most stable. So we're going to do a rotation. The little template here says keep the front the same because ethyl's still at the bottom. So no rotation for that. Now you have to arrive at a staggered conformation because that will allow the more stable one to dominate. And how are we going to get more stable? Remember, we want anti-periplanar or coplanar. So let's circle in red the biggest groups on each carbon. The front carbon, carbon 3, the biggest group is ethyl. And the back carbon, which I forgot to write this down, so I'm glad I did it here, the biggest group is propyl. We want those opposite. So let's write, ethyl's forced to be at the bottom by design of this template, so propyl we're going to put here. Now everything has to match relative. So next to propyl, so if we go clockwise around the back, going clockwise from propyl to the next bond is an H. So let's make sure we put the H on here, not there, because going clockwise from propyl around to the next bond is H. Okay, going clockwise around to the next bond from H is methyl, and that's the only one left, but it's always good to double check. Now notice this anti-relationship. Biggest group's anti. Okay, so let's answer the questions. What was the dihedral angle between the two largest groups of atoms in conformer A? So conformer A had the two biggest groups like literally on top of each other, eclipsed, coplanar. So that means they are 0 degrees. Since I said eclipsed, I'm going to also write coplanar up here. What is the dihedral angle between the two biggest groups in conformer B?